All right, this video is going to we're going to talk about Lagrange error bound. And let's take a look at a graph of a function and its Taylor polynomial. All right, so with this, the blue function here represents f of x, and the red one is the Taylor polynomial. The blue one is actually e to the x, is the one I used for this. Now, the Taylor polynomial is used to get an approximation of the value at a particular x value. And so we need to remember that this is simply an approximation. Now, the difference between the approximation and the actual value of the function, that is called your error, or the way we're going to refer to it is going to be your remainder, which simply means if you take your Taylor polynomial and add the remainder, and the remainder we will call r sub n of x, that would give you the value of the actual function at that particular x value. All right, so this is what we are going to be concentrating on right here. So this is the function that we wrote on the other page, and this says that the value of our function is going to equal the Taylor polynomial plus the remainder. And so the question then in this section is going to be, how do we find the value of this remainder? Well, one of the things we need to take into consideration is, because the Taylor polynomial is an approximation, this remainder is also going to be an approximation. Because if we knew the exact value of the remainder, we could just simply add it to this and get the original function. And we don't know the original function. All right, so this is how we can find the remainder. And just to point out a couple of things in here, this is if we're finding the remainder of, let's say, a third degree Taylor polynomial, then r sub n evaluated at whatever number that we are using. The third degree polynomial, the remainder is equal to the n plus 1 derivative. So that would be the fourth derivative if it's a third degree polynomial. Be the fourth derivative evaluated at some number z over the n plus 1 factorial times x minus a, where a is the center. If it's a Maclaurin polynomial, this would be 0, raised to the n plus 1 power. So what this really is going to come out to then, think about it in terms of your Taylor polynomial, this is going to be the value of the next term after your Taylor polynomial. All right, so let's take a look at this. Because of the difficulties in finding that number z, we're just really not going to be able to find that in most situations. The best that we can hope for is an estimate of the remainder. This may seem like settling, but it actually makes a little bit of sense. You use Taylor polynomials to approximate the values of functions that we cannot evaluate directly. We're already settling for an approximation. If we could find the exact error in our approximation, then we would be able to determine the exact value of the function simply by adding it to the approximation. If we were in a situation where we could find the exact value of the function, then why were we starting off with an approximation at all? So for example, let's say I wanted to find out what is the value of e raised to the 0.2 power. Well, with this, I could write a Taylor polynomial for e to the x, and I could plug in 0.2 for that x value, and I can get an approximation of what e is. Now, why would I do that if I knew the exact value of this? There would be no point in it. Okay? The thing is, do I know what e raised to the 0.2 is? Not without a calculator. And so how does a calculator calculate this particular value? And how much error is involved in that calculation? All right, so the first order of business then is to convert the existence-based Lagrange remainder to something we can use, and this is accomplished by this theorem, which is called the Lagrange error bound. Now, I do want to give credit to Benjamin Goldstein for the material for this series unit. I've used this for a while, and this is a really good setup for the series unit. All right, so this right here is going to be the main formula that we're going to be using for calculating the error in our problems. Now, I think it's important to remember real quick that a function is equal to the Taylor polynomial plus the remainder, which means the remainder would equal the function minus the Taylor polynomial. Now, that remainder, it is a distance, and sometimes it's above, sometimes it's below the actual function. And so what we're going to be doing is taking the absolute value of that. All right, so sometimes, and many times actually, on the AP exam, they will use both notations. Sometimes they will use this one, and sometimes they will use this one right here. Let me actually put absolute value bars around this as well. All right, so let's take a look at the first example here. We're going to go through a number of examples so you can see what we're referring to. Before I go any further, though, let's look at this m value right here. N, we know what that is. That is whatever the degree is for our polynomial. X is the number that we are evaluating the function at. A is your center of the function. But what is this m? What this m is, it is the value of the largest value of the n plus 1 derivative of our function. I'll repeat that again. M has to be more than or equal to the n plus 1 derivative of our function at some value. So it's going to be the largest value of our n plus 1 derivative. All right, so let's work this first problem out. It says use the third order Maclaurin polynomial for f of x equals sine of x to approximate sine of 0.5 and estimate the error involved in this approximation. So the first thing we need to do is write out the third order Maclaurin polynomial. All right, so we're going to blue on this. All right, so we're going to have sine of x is approximately x minus x cubed over 3 factorial. And so therefore the sine of 0.5 is going to be approximately 0.5 minus 0.5 cubed over 6, which comes out to be 0.5208 when you work that out. All right, so that is our approximation for the sine of 0.5. So what we want to do then is we want to find out, well, if that's our approximation, how accurate is this? What is our error? What's the error involved? What's the maximum of our error that we could possibly be within? And so the error then is going to come from the maximum value of the fourth derivative, because it's the next derivative after our degree of our polynomial. So it's our fourth derivative at some number z over 4 factorial times the value the number that we're evaluating at, which is 0.5 raised to the 4th power. And it's actually 0.5 minus 0 because we're centered at x equals 0. All right. Now, this right here, we're trying to find the maximum value of this derivative. Okay. All right. Well, the maximum value, where is that going to occur? Well, the maximum value is for this one is going to occur at 0.5 because 0.5 is further away from the center, which means 0.5 is going to give us a larger error than anywhere else on the interval from x to a, or from a to x, whichever the case may be. In this case, from a to x, the center to 0.5. Okay, so in that range, 0.5, when x is 0.5, that's going to give us the largest possible error. Okay, so what we're going to do then is we're going to evaluate the fourth derivative at this point. Now, one of the things to remember is that we are dealing with the sine function. Well, the first derivative of sine is cosine, and then the second derivative is negative sine, and then the fourth derivative is going to be negative, let's see, cosine, sine, negative cosine. Okay, now sine and cosine doesn't really matter because the sine and cosine function, graphically, it bounces between -1 and +1. So no matter what we are taking the sine and cosine of, the maximum value of the derivative is going to be a 1. And so this means that our error, or the maximum value of our error, or the remainder of our third degree Taylor polynomial at 0.5 has to be less than or equal to 1 over 4 factorial times 0.5 factorial raised to the 4th power, which comes out to the remainder having to be less than or equal to 1 over 384. All right, let's look at the next situation here. It says use the sixth order Maclaurin polynomial for the cosine function to approximate cosine of 2. All right, so that's the first thing that we're going to do is write out the sixth order cosine polynomial. So cosine of x is approximately equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Now what we're trying to do then is approximate the cosine of 2. Well, that would be equal to 1 minus 2 squared over 2 factorial plus 2 to the fourth power over 4 factorial minus 2 to the sixth power over 6 factorial. And what this comes out to is negative 0.4222, and a bunch of decimals after that. All right, so that's our approximation for cosine of 2. Now what we want to find is the error so that we can say our approximation has got to be in between what two values. Okay, so we got to find that error, and that error will give us the plus or minus from our approximation. All right, so how do we find that error then? Well, since this is a 6th degree Taylor polynomial, we're going to be finding a 6th degree remainder, and this is going to be evaluated at 2. And our remainder has to be less than or equal to the 7th derivative at some number that we don't know over 7 factorial times 2 minus 0 raised to the 7th power. Now, once again, what we want to think about is this right here. That is going to be a either a sine or a cosine, doesn't really matter, because the maximum value of a sine or a cosine is going to be 1. So what we can do then is we can replace this with a 1. Remember, this is our m value that we said we're using, and m stands for the maximum value of the n plus 1 derivative. And so in this situation, that is going to be 1. So we have 1 over 7 factorial. This is going to be multiplied by our 2 raised to the 7th power, and this comes out to be 0.25397. All right, so what that means is that our remainder has got to be less than or equal to this value. So the absolute value, what that actually means then is that this right here, this could equal positive this, or it could be negative this. And so this we found was this value right here. That is the cosine of 2. So if we take negative 0.4222 and add 0.25397 to that, that will give us the upper limit, and if we subtract that value from it, that will give us the lower limit. So adding 0.25397, that is going to give us negative 0.3968, and subtracting 0.25 is going to give us negative 0.4476. All right, next example says use the third degree Maclaurin polynomial for f of x is equal to e to the x to approximate the square root of e. All right, so first thing we need to do is write out the Maclaurin polynomial. Okay, so for e to the x. So e to the x is approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And so what we're trying to find then is, what is the square root of e? Well, that is the same thing as saying e raised to the 1/2 power, which means our x value is 1/2, so we can substitute that in. So we have 1 plus 1/2. 1/2 squared over 2 factorial comes out to 1/8. And then 1/2 cubed over 3 factorial comes out to 1 over 48. And that is 79 over 48, which is about 1.64583. So that's our approximation for the square root of e. So we want to find out how accurate is this. Okay? So what we do then is we need to find our remainder. So we're finding r sub 3 because this was a third degree Taylor polynomial. We're evaluating this at 1/2. And our remainder has to be less than or equal to the value of your denominator is going to be 4 factorial, because that's n plus 1 factorial. And we're going to have 1/2 minus the center, which is 0, raised to the 4th power. And then this is where people have the greatest difficulty, is trying to figure out what is going to be this number up here. What's the largest value of the n plus 1 derivative? Now, e to the x, it doesn't matter how many derivatives we take, it is still going to be e to the x. All right, so that's what we're going to think about here. Well, if our derivative is e to the x, and in this particular case, the n plus 1, that's actually going to be the 4th derivative. So I can replace that with 4th derivative, is e to the x. Well, this is going to be evaluated at 1/2, right? And so we're trying to evaluate, well, what is e to the 1/2? Well, if I knew that, I wouldn't need the remainder. So what I need to do is figure out what is the largest value that this could be. So let's think about this for a minute. 1/2 power, that would be the same thing as saying square root. Now, e, we know that is about 2.718. So what I want to do is I want to put a number in here that's going to be larger than 2.7 that I can calculate easily. Okay, and so a number that comes to mind would be 4. Well, the square root of 4 then is 2. All right. So what that tells us then is that the largest value here of our derivative is that we're going to be using 2. Okay. So our remainder has to be less than or equal to 2 divided by 4 factorial times a half raised to the 4th power. Now, what this comes out to then is going to be 1 over 192, which is 0.005208. All right. Well, to me, that's a pretty good approximation right there. Okay. All right. So the second part of this then says what degree polynomial is guaranteed to give us an error that is less than 0.001. Well, this error is not less than 0.001. It's pretty good, but it's not less than that. So what we want to do then is come up with a way of being able to calculate that. Well, if we work it out, we know that the remainder at a half, we want it to come out to be less than or equal to 0.001. Now this is less than or equal to just our formula, which is m over n plus 1 factorial times a half, because that's where we're evaluating it at, minus 0 because it's a Maclaurin, raised to the n plus 1 exponent. And if we simplify this a little bit, that would be m over 2 raised to the n plus 1 times n plus 1 factorial. Now, what we're going to do then is we're going to let m equal 2. All right, so if we do that, that gives us 2 over 2 raised to the n plus 1 times n plus 1 factorial, which we can reduce the 2 over 2 raised to the n plus 1, that will reduce to 1 over 2 raised to the n, and then times n plus 1 factorial. And we know this has to come out to less than or equal to 0.001. So probably the easiest way of doing this is to get a table of values for this, substituting some values into that table, and that's what we have down here. So if you look at the table, when n is 0, the value of this function is 1. When n is 1, 2, 3, 4. Now the first time that our value for the function comes below 0.001 is going to be over here when the n value is 4. And so that tells us then that a 4th degree Taylor polynomial is what we would have to go to in order to get an error of less than or equal to 0.001. All right, let's take a look at the next example here. For a particular solution, it is known, this information, approximate f of 2.5, and estimate the amount of error in the approximation. All right, so first thing we're going to do is build our Taylor polynomial. And so that Taylor polynomial will be f of x is approximately equal to 8 plus 5 times x minus 2. And then approximating the function at 2.5 is going to yield 8 plus 5 times 2.5 minus 2, which is 10.5. Now, estimate the error in the approximation. Well, the remainder, this is a first degree Taylor polynomial at 2.5, has to be less than or equal to, and our denominator here is going to have the n plus 1 factorial, so that's 2 factorial, times x minus a, so that's going to be 2.5 minus 2 raised to the n plus 1, so that's 2. All right, so once again, this value of m up here, this is the largest possible value of our n plus 1 derivative. All right, well, up here, they gave us that information. They said the n plus 1, which is second derivative, is less than or equal to 3. All right, so we really got it easy this time. They're telling us that this value is 3. All right, so what that gives us then is that this remainder is less than or equal to 3 over 2 factorial, which is just 3 over 2, times 1/2 raised to the second power, which would be 3/8 or 0.375.